Thank you, sir. Good evening, everybody. Today my topic is avionics systems and architecture. And on behalf of my team, Syed, Yajat, and Rupali Vipulesh, I'll be talking to you about today's avionics system and architecture. So what is avionics systems and architecture? Basically, what is avionics? So avionics is basically an electronic device specifically made for aircraft. And architecture is basically a design or a relationship between various components of electronics. And as you can see, we have a picture where it says like what are the main um, components of an aircraft. We have airframe structure, utility systems, and avionics system. So as you all know, airframe structures, we have fuselage, wings, and etc. Whereas an aircraft, because like the pilot would need flight deck display and warnings and various other recordings to fly an aircraft. Okay. Next, we have the generations of avionics architecture. So we have the first generation architecture, which was from 1940s to 1950s, and it was called independent architecture, and it was used in MiG-21. And then the other one was centralized architecture. And as it goes, we have second generation architecture, which is from 1960s to 1970s. And we have three in this generation, and it's named federated architecture, which was used in F-16, which is a fighter aircraft of US. And then we have distributed architecture and hierarchical architecture. And then we have the third generation architecture, which is from 1980s to 1990s. And it was called integrated avionics or pave pillar architecture, which was also used in F-22, which is more of a latest modern fighter jet of USA. And then we have the fourth generation architecture, which is the modern era. And we are using pave-based architecture and open system architecture. And as you can see on the right-hand side, we have a picture, a big summary of how the evolution took place in each architecture. As you can see, we have the independent avionics, then we have the federated avionics in 60s and 70s, and then slowly it got a bit, simple as integrated avionics and advanced integrated avionics. Moving on, we'll talk about in detail about disjoint architecture. It's basically the early avionics systems where standalone black boxes were used, and a functional area had like disparate desiccated SIM displays, and interconnected media is point-to-point wiring. And then we have the centralized architecture where everything was in a central computer and everything was connected to it. And signals transmitted over one-way data buses. So it was one-way, and so basically it was like simplicity one-way data buses, and it was in both ways. You can have dual way data buses also, but it was just the first generation and technology wasn't at its greatest. So, and then we have, and this is mostly used in rockets and missiles and satellites. And then moving on, we have the advantages and disadvantages of first generation architecture. The first advantage is simple design, and software can be written easily, and computers are available in readable avionics bay. This was the advantage of first generation architecture, whereas the disadvantage was the databases were like really long, and to change software in the avionics or architecture was a bit difficult. And these components were really vulnerable and could be damaged easily. And then moving on, we have the second generation architecture. And as I said, we have three architectures in this generation. The first one was federated architecture. Each system acts independently but united. That was like the federated architecture. And then data conversion occurs at the system level, and the data are sent as digital form called digital avionics information system, which makes this more reliable than the first generation. And then the distributed architecture, it has multiple processors throughout the aircraft that are designed for computing, takes on a real-time basis, as a function of mission phase or system status. And the processing is performed in the sensors and actuator. So basically, this was like distributed architecture. We had different components at different places. So each component had its own task given to it. And then we have the hierarchical architecture. It's basically like a tree topology. This architecture is derived from the federated architecture. It is based on tree topology, as I said, and most of the military avionics flying today based is on this architecture. And then moving on, we have the second generation architecture and its advantages and disadvantages. Okay. So we have the advantages as I read is digital processing provides precise solution over long range flight compared to analog avionics. So this will make things easier and precise. The solutions we'll get is a bit quicker compared to the first generation. Time division multiplex saves hundreds of wiring. So this will help us in reducing waste and making it more eco-friendly. Changes in software are easy to make. And then we have fewer shorter buses, faster program execution, overload in data is reduced. So the data can be sent immediately without any piling up of data. And the disadvantage is since there is a great diversity in the processors, this could cause problems in software. And as always, changes in software was difficult and it was vulnerable since it was second generation. And then moving on, we have third generation architecture, and it was called pay pillar architecture. So pay pillar is a generic conceptual architecture, and it was developed by USAF, specifically targeted for fighter jets, or also known as tactical fighters. Um, then it's basically used for military aircraft application. This was mainly focused on pillar architecture was mainly focused on military aircraft application. And then the main functions of this pillar architecture was digital signal processing, mission processing, vehicle management processing, avionics system control. Then moving on, we have the integrated avionics in third generation architecture. It's basically a core computer that performs the majority of avionics function. Looking inside is a computer with several modules and can be identified performing a specific function like display flight management modules and autopilot module. And the features of this integrated avionics, it is a layered architecture and it uses a simple standard programming interface layer to hide hardware and application from one another. So it is like separated so things can be well maintained. And then reconfiguration of application on the modules can be easier. This can be static configuration or dynamic configuration. The dynamic reconfiguration can be in flight and reconfiguration static while the aircraft is not in use. So this were like the simple things we could make a change in the architecture at any time. That's like the best thing of third generation architecture. And the code can be reused and portable. And then we moving on. We have the pictures on left and right, which basically says the evolution and that took place in the architecture. As you can see, we have the distributed analog, then we got distributed digital. So analog was in 1960s where we didn't even get to know about signals, and then in 1970s signals was introduced to technologies, and then we used this in the architecture and avionics systems. And then things got a little bit more complex, and after that we'll be using advanced integrated modular, which was made in 1990s, and then it got way more better as the technology boom after 2000s. And then moving on, we have the various data buses and protocols we have MIL STD 1553. It's a shared bus, and we have the various data rates to it and its applications. It's basically used for military avionics, whereas ARINC 429 is point to point, and it's bipolar RZ electrical. And we have the data rates, and it can run at the max 100 kilobits per second, and it's mostly used for commercial avionics. And then we have the various protocol also. And on the right hand side, we have an aircraft and various avionics systems used in an aircraft. We have a primary flight computer, autopilot, air data, and other flight control databases. And this is a picture where it's showing like the various communication units or antennas or protocols which are used in an aircraft. So we have ACARS, SATCOM, 4G, cabin, wireless, APs, TCAS, ADS, GNS. So there are like so many antennas and various communication units put in an aircraft, which can help the pilot in terms of simplicity. I mean, it can be useful at times. So, yeah, that's a simple thing that if we see and we can like get to know about it. I won't go in detail because it'll take a long time. So moving on. So we will talk about MILSTD. It's basically a military standard database. It is simple and deterministic, and it's really reliable. The main components for MILSTD is bus controller, remote terminal, and bus monitor. And the messages in this avionics databus is up to 3216 bits word. It is a two-sided bus, and transmission speed is 1 megabytes per second, and it is well protected from disturbance, so the data can move smoothly in the system. So yeah, and going next, we have ARINC 429. It's basically another database which is widely used for commercial aircraft. Yes, it is used for commercial aircraft, and it's a one-way flow database. So it's not two-way as MILSTD 1553. It was used in 1980s by Airbus A310 and Boeing 757 and 767s. And the new upgraded version of it is called ARINC 629, and it's a single bus, sadly. But yeah, it's better and it can transfer more faster data compared to ARINC 429. And then we have CSDB and AFDX. CSDB stands for Commercial Standard Data Bus. It is a multi-drop bus, formerly known for Collins Standard Digital Bus. It was made by Collins, and the maximum speed of this data bus is 50 kilobytes per second. And most commercial flights use this serial bus, and it is a two-wire asynchronous broadcast data transmission bus. Okay, and then we have the AFDX, which stands for Avionics Full Duplex Switch Ethernet. It's basically an Ethernet used in mostly in commercial aircraft. It is also known as ARINC 664. It's a data network patented by Airbus. The data network is based on internet technology using commercial off-the-shelf components. So commercial off-the-shelf components is basically the components which are specifically made for the company, and it's not sold separately in the market. The 6 primary aspects of an AFDX data network include full duplex redundancy, determinism, high-speed performance, switched and profile network. So yeah, and it's also used in A380 since it's an Airbus database. These are the references, and thank you so much.